Okay, hello. Today I'm planning to live code a new feature for kafka-streams-cassandra-state-store. So let's get started. I'll begin with giving some context. So today's topic is interactive queries. As I mentioned with Kafka-streams-cassandra-state-store, so we're working with Kafka Streams. Interactive queries is a feature in Kafka Streams that allows applications to query the state of stream processor, and it enables interactive access to the internal state stores of your application, which allows to perform dynamic lookups. A popular example would be to build a REST API to access your state store. And Kafka Streams Cassandra-state-store is a library implemented by me to persist data to Apache Cassandra as a drop-in replacement for the official state store solutions, which are mostly RocksDB and InMemory. And there's also a blog post which introduces the library in detail. And as you can see here, this is kind of the most basic setup to explain. And due to the nature, I will go into this in more detail with another diagram. I think that will be easier. But we want to have like an external client, let's say HTTP, to access via API our state of Kafka Streams. And with using Cassandra State Store, there's obviously not only Kafka involved, but also Cassandra or ScyllaDB, where the state stores reside. So if we want to get the data, we need to query Cassandra, essentially the database. And the main benefit, or I guess that's to be decided or assessed if it's a benefit or not, but what you not have to do using Cassandra State Store is you do not have to do RPC lookups. I think Confluent named this pattern an RPC layer. So essentially, since with the usually regular Kafka Streams, the state always is local to the instance, either RocksDB or InMemory. If the data you're looking for to satisfy your query is not in your local state, then you need to do a remote lookup to the instance that actually holds this data. And this is not required, since in Cassandra, all the data is in one place, and each instance running your Kafka Streams app has access to that same table in Cassandra. So much to build up and start with the recap. Let's look at some code. So the usual way how you get a state store for interactive queries is that you ask your streams instance for a store by name and what type of store it is. We're working on key value stores today. And then you get a ReadOnlyKeyValueStore, which you can, for example, ask to get your value for the key hello, if it's a string long key value store. And those are all the methods. So we have get, range, reverse range, all, also descending order, and a prefixScan, and approximate count. So again, I think I tried to explain already the pattern with the RPC layer. Just to use this proper example, I will make it quick. We have a topic for partitions. I color-coded the partition IDs, or the partition numbering. And with 3 instances of your Streams app, you would get an assignment where 2 of the instances get one partition each, and the third instance takes 2 partitions, 2 streams tasks. And so if you query your API, if you query for the read, like data in partition 3, and you access with a load balancer, kind of randomly access your app that holds actually data for partition 3 or task 3, then the request can be satisfied from the local state. So you do a lookup to your local state and then return your value. But if you request, say, for partition 2, here color-coded green, and you hit instance 1, which only holds partition 1, but your data is in partition 2, then you cannot find it locally. You look up metadata, and then you proxy request to your streams instance 2, which holds the state for partition 2, and then to the lookup, you get a response back to the instance 1, and then you respond back to your client. That's how you work with the usual or the common Kafka Stream state stores. And for that remote lookup, there's a pattern. So you either, obviously you could go to all other instances, or first of all, you need to know about your instance. And this is done via config, how you configure your instance using, I think I should have added it here somewhere. The application server property. So in each instance, you set your own IP and the port of your remote API, it could be REST API or gRPC or whatever. And this is then distributed to all your streams instances via metadata, via the heartbeat protocol. So if you're in our example instance 1, and you need to know where does my data for partition 2 or for the key I'm looking for, which if we say it's in partition 2, where does that reside? Then you use streams metadata for key. So this is your state store name, the key, and the serializer for the key. And then you get metadata. You can check if the host info is, if this is yourself. If it is, you get it from local. And if it's not, then you take that information from the metadata, the host and the port, and you build your protocol, like your REST API access or gRPC or other whatever protocol you implemented for your RPC, and then you do that remote lookup. This maybe to mention one more detail. This is the pattern for get by key. So if you do a single key value lookup, but there's also other query methods, interactive query ways of querying data. For example, a range query, where you say I want to get all data for the keys from A to X. Then you cannot determine which instance holds the data, because the data usually will be in split across all partitions or tasks. So you need to reach out and query all other instances. If it's 3, you need to query the 2 others and your local state. If it's 20, you need to do a remote call to 20 other instances, or to 19. And then you need to aggregate the data you get back. So there's a lot going on. If any of these is unavailable or does not respond or is slow, then there's a lot of traffic going on to satisfy and combine this data from the local state of all your instances. Now, moving on to Cassandra-State-Store. In Cassandra-State-Store, one of the benefits this might bring, among a lot of other things to consider, is that you do not need an RPC layer, as mentioned earlier. So each of the instances has access to the same Cassandra cluster and the same table, and in theory can query the table and access all the data from all tasks, and there's no need to do remote lookup between your instances. Okay, quickly think how to continue. To mention briefly, the Cassandra KeyValueStore comes with two different flavors or variants. One is called a globalKeyValueStore, where the data is persisted. So in Cassandra, you also use or have to define a primary key. The primary key consists of a partition key and a clustering key or multiple. And in the globalKeyValueStore, data is persisted without the actual the task ID, which is of the topology, and the partition ID. So it's simply using key of your message or of your key value entry key as the primary key in the Cassandra table. So it's straightforward to simply get your value by key. I think that might not be clear right now, or I would need to go in more detail or look at the table. Let's skip this for later, but what I wanted to actually say is we have two types of stores. One I call a global key value store, where the data is not partitioned by like tasks or partition IDs as it is in Kafka. And then there's also a partitioned key value store, where the data is written to the Cassandra table also using the same partition as it's in the stream task and in the topic, in the input topics. And the reason for that is if you want to do range or prefix scans, so not just a simple lookup, then this is not possible with the global key value store, simply because Cassandra does not support that way of querying data. So if you want to query the data with range and prefix scan queries, you have to use the partitioned key value store. So you say for partition 0, I want all keys from A to X. This is possible, but only when you create your table that way, where key is used in the clustering column and the partition is the partitioning key, the primary key. Okay, hope that was not too random explaining Cassandra table or how Cassandra works, but we will get to that in a bit more detail later, or maybe in a different recording. But let's quickly finish going over this blog post I published recently. For global key value store, I already have provided a way to get like a proper setup read-only key value store to access efficiently access your data. And I will start bottom up. This is provided via a cassandra-state-store, read-only global key value store, where you pass in your streams instance and the store name. Then you get whatever underlying object of the interface read-only key value store, and you can use it to access, like, get a value by key. Under the hood, this simply implements this portion of code, where we do some kind of extra logic to ensure that streams does not how to start with the nature of of your data in Kafka Streams being always split between streams tasks. So also your state stores are split. For each streams task, there's one state store. So you can have multiple threading, multiple tasks assigned to your local instance. And then there may be multiple other tasks split across other remote instances. So when you access or when you ask streams to get a store for name and type, how I explained earlier, then what you will get back from these streams is not an individual state store, but wrapping state store. And the wrapping state store wraps essentially all your local assigned state stores, which could be just one, or it could be 10 or whatever number. And then when you do lookup, like get key, whatever, ABC, then this wrapping state store essentially will iterate over all the underlying stores, because it does not know which of the store instances actually holds that data. Potentially each one of them may. So it iterates through its underlying list of state stores and then does a lookup with each. And only if you hit, if you have a hit, then it returns the data. And now the complexity with that, using that custom implementation of a Cassandra state store, and in particular the global key value store. What we do not want is, say we get by key and the key does not exist in our state. So with that wrapping key value store, problem is if you just say stream store from name and type only, then you get this wrapping state store provider, and underlying you might have a list of 10 state stores. And if the key does not exist, or if there's no value in the Cassandra table, and the wrapping store provider iterate through it, it would essentially make the same query, the exact same query to the Cassandra database 10 times, which does not make sense, because if it's not found the first time, then no of the other lookups will find the data. So it's very inefficient. So what we do, simply because the data is simply persisted differently from a regular state store, where you actually have to iterate over the stores, because each store only has the state for the partition. That's not required for the global key value store, because each store, which is that construct of Kafka Streams, still has access to all of the data, not only its own task. So we only need to do one lookup, and either the value is there or it's not. And this is achieved through simply saying we use streams metadata for local threads, and then we just take the first. Here's kind of if nothing, no threads or no tasks are assigned at all, or no active tasks are found. Now we may need to see if you have a streams instance with no assignment. I'm not sure if that actually is a valid state, or well, it could be if you run more replicas, you have partitions or streams tasks. So yeah, I think you need to do things wrong, or your Kafka cluster might not be available, or whatever problem you could run into here. But this would then also not work if you use a non-Cassandra, if you use a regular state store. So let's ignore that portion of error handling. But what we do here is we just pick the first active task, and we get the partition, which is just an integer. And then we restrict our state store. We extract simply by that partition of our first active task. And then what happens is you still get a wrapping state store back from Steam's your streams store method, but it's set up that way that it's only going to look up or use the state for your defined partition. So even if you have 10 local state stores from 10 streams threads in your instance, if you do a lookup get by key, then it will only query the Cassandra table a single time for a particular partition we defined here. And since it's the global state store, the partition for the lookup doesn't matter. So you do a query get by key to your Cassandra table and you can find the value if it's there. So this is a bit extra efficiency for the globalKeyValueStore. And this is the way how you could use it. And all of that complexity and details are hidden away and solved already. And what we actually want to do today, after that long introduction, is when writing this blog post, I noticed for the partitionedKeyValueStore, or well, not I didn't notice it. I mean, it was clear that with the current state of the kafka-streams-cassandra-state-store Cassandra-state-store library, when you work with partitionedKeyValueStores, you would still have to use that RPC layer and work the same way as you would need to with RocksDB or InMemory. But since all the instances still are able to access the same data in Cassandra, this should not be required to use the RPC layer, but if we can solve it and provide a better read-only-keyValueStore implementation, which efficiently directly queries the Cassandra table, then there's no need for that RPC layer. And this is exactly made me write up this issue as a new feature in the library on GitHub. And this is what I want to code today. Let me take a quick break and then let's start with implementing and see if we can solve this and how this turns out. Okay, after a short break, I'm back, fully refreshed, I hope. So let's start with the coding. Or actually, I just thought maybe it was too theoretical, too abstract, explaining earlier. So I'm get a quick detour and show you, in case you're not already familiar with the Cassandra-KeyValueState-store, how the underlying Cassandra tables look like, and again quickly explain the difference between the global and the partitioned state store. The first is an example for the partitioned KeyValueStore. So the table in Cassandra has columns partition, key, timestamp, value, and the value, which is blob. Key also is blob. It's all just stored as bytes, so you can persist whatever string, log, afro, protobuf, whatever Kafka streams state stores always simply persist bytes. And the partition key for the partitioned store implementation for our table is a combination with a partition as the partitioning key and the key used as the clustering key. Compaction, just read up. It's also somewhere I think in this README, I explained why a level compaction strategy is used. I'm not sure if I did, but you can just look up, and if you think there are better compaction strategies, let me know. But I think this is the default choice. But let's not go into that detail. What the key, what the point is here is the primary key is uses the partition as partitioning key and the key as the clustering key, and this allows to query, for example, get select from store where partition equals 1 and key is larger than A and smaller or equals X to do a range query, for example. And I think that's kind of the main detail for the partition. And the globalKeyValueStore simply has no partition, so you simply use the key as the primary key, so you can do a get by key, and you get your data, but you cannot do any select. You cannot do range queries or any of that. On the other hand, if you do a get by key, if you want to do a get by key for this table, you need to know the partition. So you cannot just simply select from store where key equals A. You have to say partition equals 0 and key equals A. This is the difference, but again, this is how Kafka-state-store also works, because everything is partitioned. So each lookup, you need to know your partition to access your data in RocksDB or InMemory to access the correct state store. Okay, let's go back and start now with the coding. I think here I just summarized again what I want to achieve and what I thought of to solve for the partitioned key value store is to implement ReadOnlyKeyValueStore interface with a facade that uses kind of the internal repository, or essentially the Cassandra client library to query, directly query the Cassandra table, and also combine results. Since it's partitioned, you might need to do multiple queries in parallel and then combine all your results. And all of this I want to solve with this implementation, custom implementation of ReadOnlyKeyValueStore, to avoid the need for doing any remote lookups and then combine the data, because you can do it all within your single instance, because you can access and query all data for all partitions in Cassandra directly. And this also means you still need to query by partition and then merge the results and return a key value iterator. And there I found already, it's an internal package, so I cannot access it, but I might be able to copy or reuse a similar pattern for that composite key value iterator to return to the by the interactive query method. Let me take another quick break. Okay, finally, code. Let me make this a big, so that's better readable, 125%. So I have the kafka-streams-cassandra-state-store library repository checked out, latest version of the main branch. So let's simply start with creating a branch. This is our issue number 23. And let's call this Cassandra key value. Yep, Cassandra read-only key value store. No, I think this is the Cassandra partitioned. It's a bit quite long. Okay, we have our new branch, and let's just start slowly. So here we have our main code base. It's implemented with an interface, Cassandra-state-store. Here I have, this is quite recent, was dropped with the latest, with the last version. And this is what I explained earlier. Here is, for example, that read-only globalKeyValueStore, doing this magic to ensure it's only going to do one single query and not many, multiple times the same. But for the partitioned KeyValueStore, there's no proper solution. I simply wrap the usual streams store from name and type. So this is not doing anything that would help you in any way. Just created the interface method anyway, but this is here we want to work on and return our custom facade. Okay, here the code is structured between those classes, wrapping the key value store and then using under the hood Cassandra key value store repository. And this has two implementations, the global key value store and the partitioned key value store. And the key value store implementation itself can work with both. So this is just abstracting the complexity of the state store type used. So it's simply split in kind of the streams business logic essentially, and then the data access layer working with Cassandra through that repository. Then we have our integration tests. I should have Docker running. So the way tests are implemented until now is simply through integration tests using test containers. So for example, we already have two tests that address or work with essentially interactive queries and accessing the state store. Let's just start with the global state store. Here we actually use exactly this read-only global key value store of the interface. So we get our store for passing in streams and the store name. And then we look up kind of a key that does not exist and expect it to be null. And we look up an existing key that should return data. I think the names of the variables are wrong here. Here I'm not using, just putting random words as the input. So this is the word count example used under the hood, and then expected words should be all of the above in different counts. So I think I copy pasted here a wrong number. I think this should actually be value for hello. So we get count for hello, and we expect it to be 1. Also, I think we could actually use our expected words, which would be the better choice, is equal to expected words for the key hello. And then we also test the approximate num entries, which should be equal to the expected word counts size. This is the global store, which we do not want to work on. But I think we are also using interactive queries here. And I also have a word count interactive queries test, which is using also, I think it's also using the word count example as a topology. But it's using the partitioned KeyValueStore, while that global store test uses the globalKeyValueStore. So I think I'm just first of all going to word count global KeyValueStore global enter. Is this too long? I think it might be too long. Maybe it's also better to provide multiple test files for basic test if the implementation is working or not, and then all of the interactive queries separately. But I think I will just say this is the we just name them with the same pattern, and we test both the global and the partitioned KeyValueStore. And the partitioned KeyValueStore right now, it kind of hides that complexity when you would run with multiple instances, because here in the test we just start the topology stream start. We just send in the input data, and well, in this test it's not only interactive queries, but we also use a consumer to check the output topic. So we only query the store, but we also this is just kind of to test that the library implementation is working. So we also consume the output topic and expect assert kind of if all the data is there and matches what we expect. But then we have kind of a second part of the test. Maybe it would be better to split that at some point. But right now it already exists, so I'm just going to continue to use that. We can improve on that later. Where we access, again, the read-only but the partitioned KeyValueStore to get our interactive query store. And then we do, again, also some tests. We get an unknown key, we get an existing key. Then we say we want all the data, which returns a key value iterator. And then we do prefixScan. One for Bell, where we expect it's all kind of the countries of Europe. So we expect the query to return Belgium and Belarus. And we do a prefixScan with F also, where we get Finland and France. Also a range query, so we want to get all of our values for the keys from Lithuania to Moldova. And this returns Lithuania, Luxembourg, Malta, and Moldova. And then we also do approximate number of entries and compare that to our expected word count size. So this we can simply run to make a start. To start with passing tests. Actually, we won't have to change the tests really, but we want to see how the state is accessed under the hood, or improve and make that more efficient. I think we might need extra tests, or better use unit tests and mocks under the hood, but I'm not going to do that today, but actually work on the implementation of the code itself. So the test is passing. And let's just keep it like that for a start and begin with working on the code. Okay, let's start again here, where we get our read-only-keyValueStore. And I think what we want to return here is not the default WrappingStoreProvider that Streams provides, but we need to construct our own implementation of the read-only-keyValueStore, which is different from simply the existing Cassandra-KeyValueStore that implements already read-only the interface. But we want to start here with a new class, Cassandra read-only-keyValueStore. That implements the read-only-keyValueStore. And I think same as our KeyValueStore here, it can directly implement the byte KeyValueStore. This is what we work with, and kafka-streams works with. It's implemented generic, but it's always using bytes and for the key, and then the byte array for the value. And here we have to implement all of the methods. And let me rethink that again. I think that's not exactly true what I said. The data always is persisted in bytes, but if we want to have a read-only access to the store, we want to do that. If you look at the test, we want to get not bytes, but our actual serialized or deserialized data, which in test setup is a string and long, or could be like a avro classes. So I think let's undo that and say this is, how is it called here? Yeah, well, just K. Let's keep that generic. And let's see what we might need to work here. I think we will need the streams. We need the repository. I think you'll also need the isCount all enabled. I'm not sure if you're gonna need the name, or if that will be part of the repo. Then I think we also need probably need the Kafka Streams instance. So we pass that in via constructor, and let's see where we can go with that. I think since we need to do access our repository, which stores bytes, we need also the service. So I think we need final key deserializer, and we also need to I think we need the key certain, not only to deserialize, and we need the value. So the key and the certain value, and we add them to the constructor as well. And let's simply start with the simplest, one of the simplest methods, which is the get. Well, it's actually not that simple. Let's start with the count query. Let's say we want to get the approximate num entries. In our existing KeyValueStore implementation, again, which also implements the kafka-streams-cassandra-state-store interface, which extends state-store now at KeyValueStore. The KeyValueStore itself extends the state-store and the ReadOnlyKeyValueStore. So this is why our approximate num of entries is also implemented by our KeyValueStore implementation that already exists. And since doing a select count for any database, and which also goes for Cassandra or SolarDB, can be very expensive. So if you have a big cluster and a huge number of data, doing an exact select count of all your data will be a massive load on the database. So this is why I also have provided a toggle essentially to enable the select count to avoid accidental access or usage of select count queries to your state store Cassandra database if you do not intend to enable that. So it's an opt-in toggle, which we also need to consider when we with our new implementation of read-only KeyValueStore. So essentially we just copy this here. Again, the reference, it's count all enabled. Here it's documented with count all enabled, so you need to opt in that select count is used. Unfortunately, compared to like in InMemory, you have a hash map or something underlying holding your data where you can get the size efficiently. And with RocksDB, there's it's specially implemented to return the approximate number efficiently for your local state store. But for Cassandra, there's no way to get an approximate count. So yeah, unfortunately, we either get the exact count using a select count, or we just say it's not supported and return -1. So let's copy that, and in our implementation, we say return repo get count. But now complexity is our Cassandra KeyValueStore always is a store object, one instance of the store object by each partition or each stream's task essentially. So the implementation here of this object we in the init, we get the processor context in, and essentially it's actually the state store context. And here we can extract from the taskId the partition, which is then used for accessing our Cassandra table. Now in our Cassandra read-only-keyValueStore, we don't have a particular partition, because this is exactly what we want to avoid. We want to query our state no matter where or how the data is partitioned or where the data resides. So the approximate num entries, we want the count for all of the data, not only for a single partition. And our facade here also should not only work with partitions. So what we actually need to do is here we just want, and for efficiency, again, since we want to satisfy our lookup with a single query to the state, to our Cassandra table, we simply want to do a select count star for the table, the entire table, even for the partitioned one. The logger we can just copy. But the select count we don't have with our KeyValueStore repository yet, because we only have a get count with requiring the partition. So we simply are going to add a new method to our repository. And now we need to implement that. For the global KeyValueStore, the partition already is simply ignored, for we have a select count without any query conditions. We just count all of the records and then return. So here we just need to copy and implement it the same way, essentially. I think we actually could also then just say return get count to not any duplicate code. And for the partitioned KeyValueState-store, we right now to get the correct results, if using the WrappingStoreProvider, if you would do a count star, same as with RocksDB or InMemory, you would need to do it for each partition and then sum up all of the counts for each partitioned store. Here we are actually using the partition by a select count by partition. So when we implement it here, we actually need to just to add a same select count all. So let's simply add that select count all, and it's a prepared statement. So we have to implement the query, which is used, and we just do select count from table name, and that's it. Just remove kind of that condition where partition equals the property. So we have our select count all, and this now implements the get count. Again, here with the partitioned, it's now different. It's not duplicate code, but it's actually using different queries. And in our new implementation, we now have our first method solved. So we access the repo with the total count, not for a single partition, but for the entire state, which due to the nature of Cassandra tables, we can as efficient as the database can do this, we can at least satisfy with the query. So for the partition store, we can query select count where based on the partition key, or we can do also a select count on the entire table. This is what we just implemented. Okay, that's the first method solved. Let's continue. I think the next simplest would be to do the get by key, which returns the value, not yet working with iterators or collections, essentially. So let's get started. So our repo, we have a get by key, which expects the partition and bytes, the key as in bytes. So let's start with the key. To get the key, we actually have to use our key sorter and serialize the key we get passed in. I think this returns, no, not serializer. Serialize, which takes the topic. I think the topic doesn't matter here, and pass in the key cert. Why is it complaining? Might not have been initialized. Key bytes. Okay. This returns a byte array. So I think we also need to wrap it with bytes. Wrap our byte array, and then we have our key bytes. So if we get by key, if we now get the partition, let's say we just, for the sake of completing, we say it's 0, then we can already access our repository. Now the repository returns a byte array because it's generic or using bytes only. So we need also again to use, let's say this is our value bytes. And now we say we use the value sorter deserializer and deserialize for like this. Now we are already halfway done. We can access our repo to get the key. So we serialize the key, get the value in byte array, and then we deserialize and return the value. Now what's missing is the partition. So how do we know the data resides for our key? So our key, I think I actually covered it. So here now in the blog post, what you usually do is you get the metadata for key. Let's just take that approach. So we say streams. Tree metadata for key, and I think this is an important detail. We also need to pass in the partitioner metadata for key. So we have our, did we pass in the store name? No, we did not. Let's add that first. So let's do that even before string name, add that to the constructor. So we start with the name, key, and then the partitioner. The partitioner we also do not have, so let's also pass in this should be the partitioner. This is put by under the producer. Stream partitioner. Tree partitioner. And also add that as a constructor. Okay, so we get the metadata. Key metadata. And key metadata, we can access the partition. So this should, let me take a break to look after my cat. Not sure if it's recorded on the mic or noise cancelled. But let me take a quick break, a short break. Okay, I'm back. Cat has her second breakfast. First one was too early and seems too small. Okay, where do we left off? We have at least implementation for the get value by key. Actually, not quite sure if that's going to work out, but let's then test later, and let's keep it as it is for now. Okay, now on to the more complex parts where we have to work with key value iterator. Let's start with the simplest of them, with the all, without any query conditions. Now here again, repo get all. What it expects is again the partition, but this time we cannot do a lookup partition by key, but we simply need to query, we need to iterate and get multiple queries, and then combine the results. I think we could do, yeah, like similar to the proxy entries, we could also add a new method to do a select star, select all data. But then I think we cannot do the reverse all, because our data will not be in any order, in any guaranteed order. I'm not sure how if anyone's ever using, and yeah, kind of depends on the order, but I think if you read the description of the interface method, order is not guaranteed, as by its lexicography ordering might not be represent key order, but still it does provide an all and all reverse. So I tried at least to keep it the way that well, if you use them, whatever order your data has, with the key being bytes as described here, at least the reverse all should return your data in the reversed order, then the all method. Otherwise, yeah, why would there be two different methods? I guess we could also just have thrown the unsupported operation. But I think when preparing for this feature and deciding on how to implement the library, I decided to not just do a select star, but to keep with the attempt to implement both methods. Long story short, I do not want to add a select star, but I want to stay in the partitioned context with the query against Cassandra to the table. So we need to iterate, and for that we need to know all the partitions that exist. So all the streams tasks, so kind of the number of partitions of our input topic, the highest number. And let's also see what streams has to offer. So metadata for all streams clients. Stream. Let's say what do we get here? This is then streams metadata. I think we need to flat map and say streams metadata topic partitions. So each streams instance running could also have multiple partitions assigned. So we do a flat map and return a stream of the topic partitions. Then we say map topic partition to the actual partition. I need to look after my cat again. Now she wants to go out. Back in a minute. And I'm back. Okay, now we have the topic partition. And now we could say we collect them to a set. And now we have a set of partitions. Reason for a set simply is that we might also use standby replicas, and I'm not quite sure how that actually works out. What is it explaining here? Method reference. So we don't want to have any duplicates. We want individual partitions. And I think anyway, when we combine the data, the best we can achieve is the order within a single partition. Still, I think it would be better to have a list with partitions ranging from 0 to kind of in increasing order. I think actually we could get maybe we can say we do an int map to int. Let's say we do map to int, and we simply get the max partition. Max is an optional int. Or we should always have at least a single entry in the metadata. Or let's just throw a runtime exception otherwise. And what does it complain? Supplier. let's say streams metadata client. Streams clients metadata. No stream clients metadata available. Not sure if it's even possible to run into this, but determine number of partitions. Okay, so we have our max partition. So now we can simply say we want list of integer. So we should be able to do what is it? Oh, our good old friend. Actually don't know how to spell this. Beldome. We have a for loop in stream range closed. I think we actually would need that. Well, this looks good enough. Let's just take this. So we want partition from 0 to the max partition. And we collect that to a list. Actually, Java now directly provides a to list. Thanks IntelliJ. And now we have our list of partitions. Okay, now we can say partitions, so the parallel stream here, and say we map partition to our repo, get all partition forward true. And to list? No, how would it be? No. Iterator. No, this is an iterator or a key value iterator. How to name this? Key value iterator. Let's go for that for a start and see how if we can find a better name or make it more clear. Now we have what have we got here? What was I planning to do? We simply iterate over all partitions, and we access our repository. And the repository is implemented in a streams fashion to return such a key value iterator. And now we have an iterator of iterators, and we need to combine the data. So this is where I've had already mentioned here, doing kind of the homework up front. There's a composite key value iterator, which is also used when kind of under the hood, when you do similar things, accessing the state store, where actually multiple stores, local stores results are combined. So let's just take a look at is iterate in, I'm not quite sure why, 2 Kafka streams dependencies on the class path, but this is the iterator available and it's not public. So it's an internal, only accessible within kafka-streams-state internals package. So I cannot directly use this, but I think I want to make use of, I would just gonna kind of rip it off and see if I need to modify. So we also want a composite key value iterator. Just copy the entire thing for a start. And I think the only difference is that, I'm not quite sure how to implement it. My idea was to, here. My idea was to do that forget all, which under the hood then makes a query to the Cassandra database, to do that in parallel and not sequentially, to improve the performance, and then we would iterate through the individual iterators returned one after the other, and work on the returned values. So it would first walk through all of the values returned by the query for partition 0, and then partition 1, then partition 2, and so on and so forth, until all partitions have been processed. And then we can do that essentially in the same way in the reverse order. Obviously, when using parallel stream, we get back. I think we should still, that should still keep the order. It would just run or execute the individual map step in parallel. So we would run the query against Cassandra in parallel up to whatever thread pool or threads available, the scheduler under the hood. But it should still keep the order of the initial list of integers. So I think, what do I want to get at? I think we need to modify this slightly. Store type. I'm not sure if we need to store type. Essentially, we already have our iterate of iterators. So we want to say return composite value. Why is it not found? Yeah, return new, not Kotlin or Scala. And we just want to pass in this, and that should be bytes. We also need to deserialize the data on the fly, so I think we also need to pass in key certain, and let's say we just pass in the deserialized value deserializer. Why does it complain here? Not public. Okay. Public class. And store type. I'm not sure. Okay, we need the store type. I think how this works is it holds current key value iterator, and the hasNext checks if the current is null or the current does not have a next entry, so the current iterator we're walking through. And then the store iterator, I think this is where we want to use our iterator of iterators. So let's pass in, let's simply public and create that constructor as a start. And let's just create those fields. Don't want to use that as a function. Okay. That's a bit cleaner. And then now we say key value iterator hasNext. Then the current iterator would be the key value iterator next. Okay, now provided this is obviously byte. So I think we should say this, the current is also byte array. But now when we get the next key value, we need to now finally deserialize the data. So we say key value pair, and now we say we use the current next is a key value for byte, and now we can say we create a new pair where we say key deserialize topic null and next key, and the same with the value deserialize null next value, and to deserialize expects byte array. So the key is bytes object, where with get you get the byte array, and that's it. So we have here we deserialize our next key value from byte using our deserializers, our asserters passed in. And this is, I think, or should be our composite key value iterator. And that works the way that you pass in an iterator of key value iterators, and it walks through all of them until there's no next of the internal iterator, and then we move on to the next iterator. And yeah, this is, I'm not sure if this is perfectly elegant, but it should at least work. for now. So now we do have that the next method implemented. Raw use of parameterized class. Okay. Now let's let me look at this again and see if you now would want to implement the reverse all what we would need to change. Let's simply say we move this up into our constructor. Let's just make the private init method, and let's move the partitions because we're gonna need those in other places. Well, let's do it. Let's not do the init method. Let's just do it here. Static. Why is it static? Well, what we need to do it right click in the constructor. Let's just not do an init method. Okay, so we create the partitions, and then let's just say we also want partitions reverse partitions. Now what's more closed. Being lazy. Need. Oops. Is there nothing better? Actions reverse. Well, that looks better. How does it work? No. Pattern. Oh, okay. At least, anyway, that should do the trick. and we just do it in the constructor to have to do it only once. Okay, I was trying to refactor slightly, so let's start with, say, all internal, pass in a Boolean forward. And we say if it's forward, use partitions. If not, use reverse partitions. And we also pass it in here. And now we can use all internal true. And we can use all internal false. Let's move that up. I think there's a hotkey for this, but I can't remember. Okay, next method is implemented. Let's see, is there anything we can filter, refactor? I think we might need this again, so let's make this say to composite iterator, because the deserializer will always be the same, so we just pass in key value iterator. And let's just continue with our next method. Let's take the range query. So I think we would pretty much do the same as here, just that we don't use a get all, but we use a get for range. Also with the partition. And bytes from, bytes to, forward, and so we would need to, same as with the get, we would need to serialize our key. I think we can also say we say key to key as bytes, or let's say we do serialize key. So we do serialize key from, serialize key to, forward true, inclusive true. Let me check if that's the right way to do it. Here in our original key value store for the range query, we say inclusive true. Okay, that should be fine. Okay, now I think this, let's compare this with, we also need to do the forward and kind of backward. And I think the only difference is really the map function. So here we have function integer key value iterator. Let's see, can we not make this more clever? I think it would be, let's say this is our pattern. Let's create a method that returns query. We pass in the query function and it return a composite key value iterator, and we call this query all partitions. And in here, and so the query function, and we also pass in Boolean forward. And instead of the query all internal, let's copy this, and now instead of, let's just start with that same, and instead of the, where did I put this in? Okay, let's just pass in apply it. Okay, query function apply, so we apply function passed in. So I think we should be able to, instead of using this all internal, we can just say query all partitions, pass in true, forward true, and so we pass in the lambda to access our repository. And also if it's forward or backward, so it's double kind of twice here, but it's used for different things. So this is actually passed into the repo to query ascending or in descending order, and this is used to use, well, the partitions in a iterated partitions in ascending or descending order. So we can do this also for the reverse. Then we don't need this any longer. And for the, don't need this, we are still using this. I'm not quite sure if that's now still required as a method. I think we could do this inline maybe. Let's see if we still need this in any other place, but I think we should be able to use this now for all of the other range or key value or the iterator queries. So sorry, where we starting on the range query. So essentially we can say read query all partitions, repo. Sorry, what have we had here? I think I did delete that bit quick. I think we already had it implemented. I think we just pass in this. Return query all partitions and forward true. And the same for the reverse range just forward false. Okay, this looks, I think, okay. Almost the same code here, but I'm not sure if it's worth to really extract that into an internal method. Let's keep it like that for now. And I think the only more method left is the prefixScan. So again, I think we can prefix serializer. Let's start this. Prefix always is forward only. Not sure why. For the others, there's a reverse also, but for the prefixScan not. But that's how it is. I'm not gonna challenge that. But now we just do repo range. Right. This is also using a range query actually. So let's look at our original implementation for the prefixScan. How that's done under the hood, also for RocksDB and in the original Kafka Streams code base. It's some small magic based on bytes. So we essentially can just copy that, and then it's another range query from to inclusive false, forward true. So let's get a from and to in bytes, and then take our range query, just passing in from and to, inclusive false. That's the only difference. Forward, and that's our prefixScan. So I think we are all done with the Cassandra ReadOnlyKeyValueStore, and we're using everything that we passed in. I think that's kind of at least a stable state of the implementation. So let's move on and start to actually use it, and yeah, take that next step. So actually, I'm just gonna copy and say just keep the original method, and let's do it the other way around. Let's a new I think we need to pass in more data anyway. So return new y, and need to pass in streams. Isn't there any better way to do, like, okay, hover does the trick. Okay, streams, the name, we also have the store. Then comes the repo. New partitioned. Then comes is called all enabled. This actually we're gonna also pass in here, because we cannot determine it ourselves. What else have we had? Key-sorter, value-sorter, and the partitioner. I think we also need to pass those through. Just call X, Y. Why did I use X, Y and not? Let's just try to. It's used here as well. Okay, let's keep X, Y for now. Maybe I will change that later. Insert the value, insert the partitioner. Now, I think that's not required. And now onto the partitioned KeyValueStore repo. Pass in the CQL session. Ooh, I think that we would also need to pass in here. How did I pass that into the Cassandra stores? Always as the first. Oh, it's passed in directly. Yeah, let's make it the first argument. Or the second, I'm not sure. Streams or session. It's not, doesn't matter too much, but let's keep it as a first. So we pass in the session. And the table name. Well, here it gets a bit tricky, for this is usually not to be used directly, so it's used under the hood. And we have that builder pattern for the key value store. So let's see if that's we need to copy and do the same with the execution profiles and all of that. It's not ideal, but let's get it working first and see if the implementation works. But what I want to get at is in the stores for the key, when we create finally partition key value store. Here we also have the resolve table name. Where we use the table name function. So we would need to pass that in as well if it's customized. So this is where it's all a bit, we would need to use a builder as well, or maybe I should drop this table name function to say we want a different naming pattern. Also adding the key space. Well, let's work with the defaults for a start. Here. So as a table name, we say we use the default store name to lowercase. I think we actually also need the key space to be safe. Let's make a yeah, it's too many. I will keep it as a to-do and address later. Otherwise, it's getting too many. We're getting lost in detail. Let's continue using the default, for that's also not customized in our tests. Okay, so session table name create table is false. That's not going to be used. Table options also empty, for we do not create the table. The data definition language execution profile, we can pass in an empty string, for again we're not creating or creating a new table. And the data modeling language execution profile, that's actually we should pass through. Also not ideal. Okay, let's say we pass all of that through, then at least we are now with compiling state. But the downside, or what's somewhat ugly, is that we have to pass in quite a lot information or a lot of properties to get this read-only partitioned key-value-store in comparison to the usual way of doing this. And I think let's simplify the partitioner. Let's just say we return read-only that did not work. Default streams partitioner. And the key serializer is so we overload the method. So we do not need to pass in the default streams partitioner, but you can also pass it in. We might need to refactor more parts of this, but let's start with this. And I think that makes the implementation complete. So now we can, instead of using this default method, we are going to use the complex one, our new one. So we also have, okay, here we pass in stream store name. Maybe we should change the order. Paste. Let's make it in this order. Okay, so we say streams, store name, session, key space. To define the key space, Cassandra key space. Count all enabled true. DML execution profile. I don't think we defined that, so we use the default, which is none. So we just say empty string key sorter. Our key sorter is a string sorter, and we have our long sorter, and that's it. So let's run this and see what happens. Okay, tests failed. DDL execution profile cannot be blank. Okay, I think it has to be null. So we also have to pass in null here. Let's try that again. So this is checked here. And it should be null, but it should not be blank, because it's only going to be applied if it's not null. Not sure if an optional would have been more elegant, but an optional can also be blank. So yeah, okay, we failed again. No streams clients metadata available determine number of partitions. Okay, now we actually did run into this runtime exception. Which we should not have. Let's run this in debug mode and take a brief look what's happening here. Why do we not have any metadata? Some old debug points. Okay. Okay, now we have our streams instance, and let's just step into the metadata. How does this work? How do I select? Oops. Just step in here. 3.5. Okay, I did step in. Okay. Validate is running or rebalancing. Seems to pass. So streams metadata state. Okay, this does not look good. Streams metadata state should not be like filled with unavailable host and port -1. My host info. I think I do get an idea what's missing here, which is when we find our streams instance, I think this is part of the abstract. Here. Abstract integration test. Okay, here. Streams properties. I think here we need to say application server config, let's say this is just any test. 1, 2, 3, 4. Just pass in anything. And let's rerun our test. Let's see if that makes a difference. I think I have seen this before. Let's see if my guess works out, and then did I set a debug point in? Let's step into again. There was still a debug point here. Okay. Okay, this looks better. So now we have a streams metadata state where we have also our host info. And I think that should also provide us with all the remaining. Probably we are the only instance, so it's only a single instance. But let's just say we step out. Okay, now we did not throw an exception, but we have our max partition, which is partition 5, which fits our test setup. Not sure where it's defined. I think it should be probably in here. Topics. Okay, input topic partitions, partition 6. So 6 partitions we define for our test setup when we create input and output topics. So 6 partitions. So the max or the highest partition is partition 5. If we continue now, we have our list of partitions, and the reverse partitions did not work. This should be in reverse order. Why is it not? Tails, but it's returning void. It's not been reversed yet. Okay, now the reverse partitions is in the right order. I think ideally this should be immutable. That's an array list. Okay, here we have an immutable. Yeah, let's change that quickly. I mean, it's not really necessary, but okay, collections. Does this exist? No. Okay. Embarrassing. Java list of list. List to okay, we need to go via an array. Do we have Guava on the class path? Copy of. We do. Maybe we should just have used another range. Can we use or just a stream? I don't know. It's not really that important. Okay, let's just first get the code working. Let's see if we can improve the code and polish later. So let me just disable all debugging points and run the entire test again. Let's see if that adding the properties for the server. So this application server config, this is what's required when you use the RPC layer to get this metadata by key to then query your remote, or first compare and then query the remote state if it's not a local, it's not assigned locally. And now we have a working test. This is good news. Essentially, this is a working state of the new feature. It's just very annoying that to read that metadata, we actually do need to now configure the application server config if it's not used. But there's no metadata without. This is not ideal, but let's quickly recap and see where we are. So we did change to kind of a more complex way to set up and get our read-only-KeyValueStore, which was also expected. That's not a surprise. This is what we need to pay for the more efficient underlying facade. Because we need not only the streams and the store name, we will not get an existing store object from our streams instance or multiple, but we will create a new facade that will create a repository and use that under the hood to directly query Cassandra and not go via kind of the interactive query interface of the native state store logic of kafka-streams. So we bypass that with our custom implementation. So we pass in stream, store name, session, key space, count all enabled. We can also explicitly configure for our state store for that facade. We can pass in a DML execution profile if we have configured one in the SQL schema. I think I did use it or explain it somewhere. An example. Here, as an example, you can you can define execution profiles for your Cassandra client driver. So you can say for DML, you can name this apples and define like local quorum or quorum, your consistency level. You can modify whatever you want, and then this is what this execution profile here is, and you have to configure that accordingly to match your Cassandra cluster and your needs of timeouts and all the other properties you can set. If you pass in null, then it's just using the defaults. And we pass in our service, which is required because usually Kafka Streams does the serialization for us, because we already have defined the service when we created the store. Down here, we create the stores via the builder, and then for the materialized, we pass in our service, and then Kafka Streams is doing that under the hood with that wrapping state store. But with our custom implementation, we have to do it ourselves. So we pass in the service as well. And I think the most annoying part is that We also need to pass in the key space. I mean, this is, I guess, okay, but it's still not ideal, but we cannot get the key space information from anywhere else. And when we create, under the hood, create a new repo, I think the table name here also is, here we now are not using the same name function as in the builder. So we can customize with table name function if we need to. I'm not sure if this is overkill, because we can just say this is how tables are named, and then we won't have that complexity to pass it in here as well. Since the default is currently maintained not in the repo, but in our KeyValueStore, I think it should be here, not in the repo. Cassandra stores, not in the Cassandra stores, in this kind of provider class with the static functions. Maybe we can make that public as a default. Maybe we can use it to the interface. Maybe we can move that to the interface and say we have a default public static, always public static file. Function string. How did I call it? Table name. And then we can use it in here as well. I think we also added the key space. This is still not. This is still not great. Maybe I would need to refactor that result table. Maybe that should be part of the function. Right. Where was I? Here. I think we can just make it, this is then the table name, key space. Let's call it full table name. also make it customizable. Same as the partitioner. Store name for table name is then, if key space is not null, then we use the full table name here. Now we still have kind of our duplicate code here. Okay, so let's say we also say we provide a default. So either you use the slightly simplified method, overloaded method, or you need to define like everything, including the table name function and the partitioner. Okay, I think that's at least one. A small improvement. Did we break anything? No, we did not change the full structure. Let's just rerun the test quickly, see if everything is still working. Okay, still passes. I think what's now bugging me is that we need to define the application server config, and then it's not while it's not even used for anything, but it's required just to get the metadata. Let's say we want to drop this and we don't want to have to do this. There should be a better way. And this is used only in the constructor to be able to get the metadata to get the number of streams tasks or of partitions of our topology. I guess we could also pass that in and expect when you request for that read-only Cassandra, that Cassandra partition read-only store to also just provide how many partitions we're working with, but then you would also always need to pass that through. If you have different environments, you might not have the same number of partitions. You can have it static. This is not an option. It should be dynamic. But I think unfortunately local store partition legs state only is shutdown started, running a rebalancing. Metadata we can only get for all clients. Query metadata for key. Streams metadata for store. Local threads, then we won't get all partitions metadata. Unfortunately, Streams does not provide access to its internals where we can determine the number of streams tasks. metadata. Topology metadata. Mm, I think it's used here. I think it's also used here. Query metadata for key. I'm not sure if I can get rid of this. Sorry, where did I add this? Here. Let's keep it for now. And I think actually I'm running out of time. So I think we need to stick with this for the recording, and let's see if I can come up with anything or any way to get hold of the number of partitions dynamically from the streams. And I think it's also required here, metadata for key. I think here actually we should be able to also use the partitioner directly. We actually don't need the metadata. We don't need the host, which we usually do when we use a state store for remote access, but we only want the partition. So let's see, the partitioner is passed through all the way through all of those streams methods. And I think here it's finally get partition apply. Partitioner partitions returns an optional set of integer. I'm not quite sure what the topic is used for. Maybe it can be used. Oh, but why the topic with most partitions? I'm not sure why we would need that. I guess you could try the partitioner that also considers the topic. I think the default partitioner definitely does not use the topic, but it uses it for the key serializer. Topic is associated with data. I think in all of the tests I've been doing, everything I've been working with, I don't think the topic was used. Well, I guess you can make use of the topic. Okay, not sure if we can do that, but what did I want to do? I think it did not keep those. Oh, IntelliJ. Okay, let's start to walk through again. Here, okay, so partitioner, partitions, and then we have that get partition, maybe multicast partitions. Okay, let's try to just this off and do this manually. Let's say private. Essentially, this is what we want to have. Partition or key. And in here, instead of this code, we want to say partitioner, partitions. We say we do not pass in the topic. The value is not required. The max partitions. We do have our partitions size we determine on init. And now we have this weird optional set of partitions. Partitions. Let's just put it like this. And now we said we can use this function with checking if it's present. If the size does not equal 1, then it's an illegal state. Obviously this is private. And then we return get iterator next. So the first entry of the set, which is optional. And we just check that it's present and has a size of 1. So we can do that now also in here. So this is our optional integer set. To null. If it's empty, to -1. Oops. Sure, if we can work with null or not, it also requires an int. Let's just say -1. I'm not sure if how could it not be present if the partitioner cannot resolve the partition for a key. Then we would use default. No, this is also not. I think we can also throw be present. Stick with closer to where we copied this from. Let's see if this still works. Okay, this is still working. Now we do not need the streams instance when we get with the get by key, because we only use the partitioner, but we also use the partitions which we resolve initially. But I think this essentially means we can just remove. I think the name here is also not. You can see those are both not used. So I think we can drop them. And we simply name is also not used. not used at all. The streams we still need to get the metadata upon construction, but the name is also not required. That means we can drop the name. So we only need the name in here in our interface. We provide that static helper method where we need the name to resolve the table name, which we use to create the full table name, including key space, when we pass that into the repository. So the name of the store itself no longer required in our new class. So we got rid of a few unused details. And I think that's a state where I will need to stop for today. And I think at least it's a state where we have achieved the working version of the feature implemented. Obviously, what's missing is documentation. I'm not sure if additional tests would be good. I just modified the existing ones. It's still not ideal. Let's add a to-do here. Sorry, where is this? This is used in needed for it's used here or needed here. And here's the question, how to return streams tasks. Okay, I think that's it. We rerun all tests, be sure that this is working, and I think that's a state where I need to stop for today. And I will put that into a pull request and see if I'm gonna merge this and add documentation and see if there's anything left to polish and optimize. And then, if that will make it for the next minor version release of the library. I think it's a bit complex to actually use because, now also there's need to set the application server config. So this is doable. I think it only needs to be, it cannot be the same for all instances, so it needs to be actually using like unique values for each replica you're running of your streams instance. And this obviously makes it slightly more complex, and there's a bit overhead passing in like key space and DML execution profile if used. Let me think if there's a better way to define all of that up front and then reuse, maybe, instead of having to define or use the same here and also down here, like the key space and table name function and DML. Okay, tests are all passing. I think I'm actually just going to commit this. 23. Okay. Okay, here it is. You can find it on the repo. Take a look, provide feedback. Okay, I'm going to wrap up with this. Thanks for tuning in. See you next time. Take care and off.